Hello everyone, I am Bhuvaneshwari, practicing at Jesus College of Arts, Commerce and Science. Today I am presenting about chemical equilibrium. Firstly, let us know about equilibrium, a state in which opposing forces or influences are balanced. Equilibrium has two categories of classification. First classification are physical and chemical equilibrium. In physical equilibrium, reactant and products are same, but there is a change in physical state like solid to liquid, liquid to vapor, vapor to solid. In chemical equilibrium, reactant and products are different in chemical natures. The second categories are homogeneous equilibrium and heterogeneous equilibrium. In homogeneous equilibrium, reactant and products are in same phase. In heterogeneous equilibrium, by taking this example, if you use this reaction in open vessel, it will be okay for forward reaction. But while doing the backward reaction, carbon dioxide is very important to get the product again. So we used it in closed vessel. Let us move on to the topic chemical reactions and the rate concept. Firstly, the rate concept. The general reaction will be written as in this form. At equilibrium, the rate of forward reaction is equal to the rate of backward reaction. In equilibrium, the speed it takes in forward reaction, the same or equal speed will going to take place in the backward reaction. The rate of the reaction written as in this format, where the Kf is known as the rate of forward reaction and Kb is known as the rate of backward reaction. Forward A and B are forward reactant and C and D are backward. By rearranging the equation, we get the equilibrium constant equation. At equilibrium, all macroscopic properties of the system stop changing with time. Equilibrium is dynamic in nature. It's not like if the properties is not changing, all the system will going to stop. The reaction is going on in microscopic level and the particles are still colliding with each other and converts into reactant to product. How much the product formed simultaneously, the same amount of reactants are there. The net charge will be zero. Is it is in the rest form? No. If the net charge is not there, it doesn't mean the moment is not there. The reactant and the product are in forward and backward direction. It is dynamic in nature, but output net is zero. Let's move on to the graph. The first graph is about rate versus time. In this graph, the forward reaction is getting decreased and the backward reaction is getting increased and merged in at one point. In second graph, it is about concentration versus time. The reactant is decreasing at one point, it is constant. The product is increasing at one point, it is also constant. It is crossing one each other. In other graph, it's not crossing each other because it's depend on the given condition of concentration. But the main thing is concentration will be constant at one point. The equation can be achieved from either side or either direction. The reactant to product, product to reactant or product plus reactant, but it will give the equilibrium point. The next is Gibbs free energy and the equilibrium constant. A catalyst only changes the speed with which equilibrium is attained, not the equilibrium constant. By using catalyst, reaction will get faster. There is no change in equilibrium constant value. At equilibrium, delta G is equal to 0. We know that delta G naught is equal to minus 2.303 RT log base 10 K, where delta Gr is the change in equilibrium for a particular reaction. Dou G by dou Xi with respect to pressure and time is state that the rate of change of Gibbs energy with respect to extent of reaction, where the delta Rg is the slope of the graph of Gibbs free energy plotted against the extent of reaction, or is the difference between the chemical potential, the partial molar Gibbs free energy of the reactants and the product of the composition of reaction mixture. Gm of the product minus Gm of the reactant where the m refers to the molar. For the reaction A to B, mu A minus mu B is equal to, we get this reaction where the mu A and B are the chemical potentials. When the reaction is spontaneous, when mu A is greater than mu B, and the reaction is non-spontaneous where mu A is lesser than mu B. At equilibrium, when reaction is mu A is equal to mu. By looking into the completion graph, it is completing the 100% of the reaction. In reversible graph, it is giving the equilibrium point before going to complete the 100% of the reaction. In this equation, Kp means the equilibrium in pressure, Kc means equilibrium in concentration. The units of Kp is atmospheric pressure to the power of delta Nc. Units of Kc is mole per liter to the power delta Nc. Units of Kx is unitless. This equation is the stoichiometric coefficient where the Qc is reaction quotient. When Q increases as reaction goes forward direction. Qc is lesser than equilibrium constant is known as forward direction. When Qc is greater than equilibrium constant is known as backward direction. Magnitude of equilibrium constant. It is high when it is greater than 10 to the power of 3. It is low when it is lesser than 10 to the power of minus 2. Equilibrium constant does not depend on the concentration of variation, reactant, product, presence of catalyst, pressure, volume. It depends only on the temperature. Variation of equilibrium constant with temperature was given by ones of equation. As per Gibbs-Helmholtz equation, we get this equation by substituting delta G star of T. We get the final equation. If the delta H naught is greater than 0, then equilibrium in pressure increases with temperature. If delta H naught is lesser than 0, then the equilibrium in pressure decreases with temperature. In this graph, if the endothermic is negative in nature and exothermic is positive in nature, you will get the slope like this, and the final equation will be like this. And the next is decomposition of equilibrium constant. We get this equation in equilibrium constant where the total moles of equation is equal to A minus X, and we will get A of 1 plus N minus 1 into alpha. Mass of reactant is equal to mass of entry system, and also vapor density is equal to molecular weight divided by 2, where capital D divided by small d is equal to 1 plus of N minus 1 into alpha, where capital D is equal to vapor density before dissociation and small d is equal to vapor density after dissociation. And the next is important term, Le-Chatterley's principle. If a system of equilibrium is subjected to a disturbance or stress that changes any of the factors that determines the state of equilibrium, the system will react in such a way as to minimize the effect of this disturbance. The next is effect of concentration. When the reaction increases, it will be in forward direction. When the reaction decreases, it will be in backward direction. Similarly, when the product increases, it will be in forward direction, and when the product decreases, it will be in backward direction. The effect of volume changes. When volume increases, pressure decreases. In this homogeneous reaction, when the volume increases, it will be in backward direction. In the heterogeneous equation, when the volume increases, it will be in forward direction. In the chemical equilibrium equation, the volume increases or decreases, there is no change in direction. Additional of inert gases. At constant volume, there is no change. Example, when we add helium to nitrogen, helium or ammonium gas container, there is no changes in the constant value. But the partial pressure of any component hasn't changed. At constant pressure, the volume increases. The reaction where gaseous moles are greater. When we add inert gas to the homogeneous equilibrium equation, it will be in backward direction. When we add inert gas to the heterogeneous equilibrium equation, it will be forward direction. When we add it to this reaction, there is no changes. Applications of chemical equilibrium. It optimizing the reaction condition, understanding drug interaction, analyzing chemical reactions. By this session, we get to know how the forward and backward reactions are resulting the net charge in concentration and reactant product. Thank you.